Hello everyone, welcome to this video. In this video, we'll be looking at another example for group isomorphism. So let's consider this group, the group of all 2 cross 2 real matrices which all have the determinant as 1. So this is the special linear group having order 2 and whose entries are taken from the set of real numbers, right? So this group is isomorphic to itself. How this is so? We can define some mapping. Say we are calling it to be phi of M, where what is this M? M is again some 2 cross 2 real matrix having determinant 1. So we are taking M from this group only, right? G only, which is special linear group having order 2 and the entries are taken from the set of real numbers. So we are defining this mapping phi, right? Phi of M from the group G to the group G, right, such that when we apply it onto A, where what is A is some member in G, that means it is again a 2 cross 2 matrix having determinant 1 with real entries. So the resultant would be M into A into M inverse. So this is the mapping. Now we wanted to prove that this mapping forms an isomorphism. So for that we need to prove that first of all this mapping forms a function. We also need to show this thing. Then we will show that it is 1 1. Then we will show that it is onto, and then we will show that it is operation preserving. So when we are done proving all these 4 properties, then we can say that the mapping phi forms an isomorphism between the group G to the group G, right? So let's see here. In the first step, we wanted to show that it forms a function. For that, we wanted to show that for every element A here in the group G, we have some association here in the group G, right? So we will show that if phi M A is some element in G, whenever A is element of G, right? So here, for proving that phi M A is a member of G, we will prove that its determinant is equal to 1. If that is so, then we can say it belongs to G. So let's take the determinant of phi M of A. So what is phi M of A? It is M A M inverse according to the definition that we have defined over here, right? So determinant of M A M inverse is evaluated when we separate out the terms. So it will give us determinant of M, determinant of A, and the determinant of M inverse. So it will give us here the value 1, the value 1, the value 1 inverse, because M is also a member of G, so therefore its determinant is 1. A is also a member of G, its determinant is also equal to 1, so which comes out to be 1. So therefore we have its determinant as equal to 1. So therefore this phi M of A is the member of G, right? Moving forward, we need to prove that phi M is 1 1. So how can we prove that? We can take 2 different elements from the image as equal, and we will prove that A and B are also equal to each other. So now if we take A and B from the set G and phi M A is equal to phi M B, then according to definition phi M A is M A M inverse, and according to definition this phi M B is M B M inverse. Now by the left cancellation law, this M and M, they cancel each other's effect, because if you multiply it with M inverse on both sides, M inverse M would give you identity. So therefore you just have A M inverse is equal to B M inverse. Similarly, by the right cancellation law, if you multiply both sides by the M, you would have M into M inverse as identity, so you would have A is equal to B. So we started with this equality and we obtained this equality here, so therefore we can say phi M is 1 1. Next we need to prove that phi M is onto, right? So let's do that. Suppose we take some element B, which is some 2 cross 2 matrix with determinant 1 from the group G. Now in order to prove that it is onto, what we should do, we should find a matrix A in G such that phi M of A is B. Now this is given to us, we need to find what is this A, right? And are we able to find this A for every B? So let's do that and see how this is performed. So suppose that this matrix A, this exists, right? If this exists, so therefore it should have this property that by definition phi m a would give us m a m inverse is equal to b. Now using this relation here, can we find out the value of a in terms of b? Yes, we can. So when we solve it for the value of a, we can have we can multiply m inverse on both sides, so we have this thing. So this and this cancels each out effect and give us identity, right? If we multiply with m on both sides, so therefore this and this cancel out each other effects, giving us identity. So we have a is equal to m inverse b into m. So this is what we have after solving this equation. So therefore we say whenever we take some b in G, we have a of this kind present in G such that phi m of a is equal to b. So let's verify whether our calculation is correct or not. So let's consider phi m of a, substitute the value from the definition, so it is m a m inverse. Now we can substitute the value of a here, which is m inverse b m, right? Now you can use the associativity property. Why? Because we are present in groups. So therefore this could be written like this and this could be written like this. We just have to adjust the brackets. So this one would give us identity, this one also give us identity. So identity into b into identity is just b. So you saw we have phi m of a is equal to b whenever b was given to us. So therefore phi m is onto. Next we need to prove that this mapping is also an operation preserving mapping. So for that, what we have to prove? We have to prove that phi m of ab, this is equal to phi m of a multiplied with phi m of b, because here the operation is just matrix multiplication, right? So let's consider the left hand side. Let's consider two matrices A and B taken from G. So let's take the left hand side phi m of AB. So by definition it is m AB m inverse, right? So what you can do, you can write this thing as m a I B m inverse, because I is the identity matrix. Now in place of I, you may write this to be m inverse m b m inverse. So this is what I have written. I have inserted one identity over here and written down its value as m inverse m. Right now what we can do, we can use the associativity property and shift the brackets like this. So the first bracket here give us m a m inverse, which is your phi m of a, and the second bracket here give us m b m inverse, which is phi m of b, so which is your right hand side. So therefore we have the operation preserving property in this case, and hence because all the four properties they hold for the mapping phi, we can say that it forms an isomorphism. So I hope you understood this example. Well, that is it for this video. Thank you for watching.